the electric potential V. In general, if we have a small charge, capital Q, at the position A, this charge will create at any point in the medium a field. At this point, we have, at this point 1, we have E1 will be out because Q is positive. At this point 2, we have E2. So I need just one charge to create the field outside. Now, in the case of the electric potential, we have the same situation. This charge will create at any point outside an electric potential V. At this point, let's say point B, for example, we have VB. At this point, we have VC. At this point 1, we have V1. Okay? V, it's a scalar quantity. The magnitude of V in general equals to K times Q divided by the distance between. Here, between AB. Here, so in the case of VB, equals to K Q divided by R AB. In the case of C, KQ divided by AC. Okay? It's a scalar quantity. If Q is positive, we will get a positive electric potential. So if Q is negative, we will get a negative electric potential. So here, if Q is positive, so V will be positive. If Q is negative, V, it will be negative. And you will add the summation of the potential, electric potential, like a scalar quantity. Okay. Now, I want to find the relation between the electric potential energy U and the electric potential V. Initially, I have a charge at infinity. This charge is small q. It's a positive charge. This system, with this configuration, we have U1. We have U1 as charge, as electric potential energy. And you know, U1 equals to K Q times Q divided by the distance between at infinity. The distance between A and D, R A D, equals to infinity. So here we get zero value. And you know, because we don't have an interaction between capital Q and the small q, we don't have forces, and the condition to have an electric potential energy, we must have an electric force between the charges. Okay? As we don't have U. Okay. If I put this charge, I push this charge from infinity to the point B. So here we have a new configuration. We have system U2, a new system. Okay. What can we say? Delta U equals to Q, the displaced one, times delta V. Okay. Delta U equals to Q times delta V. Let me say delta U. Delta U is U2 minus U1. So we can say U2, U final, minus U1 equals to Q V2 minus V1. V2 is the V as a point B. V2 is the V as a point B. We can say here V as a point B. And V1 is at infinity, the initial one. So delta U equals to Q VB minus V infinity. And also, you know, U1 equals to 0. In this case, maybe another case you have a value. So, you know, if you have at infinity VD and VD equals to K times Q, this charge, divided by the distance infinity. Also, V at infinity equals to 0. We can say delta U of the system equals Q times delta V. In this case, V infinity equals to O. We can say times VB. What I mean? Look, if I put a charge at B, delta U of the system equals to the added charge, the displaced charge, times VB. Okay, this is the difference. If I put this charge at C, okay, this one at B. If I put it at C, we will get delta U equals Q times VC. It's the same at any point you want. So we will get Q times the existed electric potential. For example, let's say now this system here has U2 as electric potential energy. Okay. Okay, let me clean before. Here I have capital Q. Here I have small q. For this system, we have U1. U1 equals to K Q times Q divided by the distance between these points. Here we have A, here we have B. So between A and B. VB equals to K Q, the effect of this one at the point B, equals K Q divided by RAB. Okay. Here we have a point C. V as a point C equals the effect of this one plus this one at the point C. So here we get VC equals to K Q divided by R AC plus K Q divided by R BC. If you have Q positive or negative, anyway, you can add these values, okay, directly. Okay, if we have a charge here, let's say we have Q prime. Find the electric potential as a point B. So, as a point B, we will get the effect of this one plus this one at the point B. Here we will get K Q divided by R AB plus K Q prime divided by R B C at the point B. If we have a charge here, Q double prime, so at the point B, we have the effect of this one plus this one plus this one. So we add here K Q double prime divided by R. Let's say we have here D R D B. So like this we can calculate the electric potential of many points at any position. So VB is related to a position. At any position, we can calculate the electric potential at any position. If I want to calculate the V at the point A, so here we have to add the effect of Q prime, of Q double prime, and Q. So we have K Q prime R CA plus K Q double prime R AD plus K Q AB and so on. Okay. And now I am solving a small examples just to understand the physical meaning of the electric potential. Let's say now we have Q as a position A. We have Q prime at the position B, and we have a point here, just a point, okay, at the position C. So V as a point C total equals to the effect of this one plus this one equals to K Q divided by R AC plus K Q prime divided by R B C. Okay, now here we have VC. This system has a potential energy, electrical potential energy U1. So here we have U1 equals to K. We have only two charges. So we have K Q prime divided by the distance between A and B. We have only this one. Let's say we have also a charge here. Q double prime. Okay. In this case, I need to add to VC K Q double prime divided by R DC, and also here we have to add another thing. For the electric potential is the effect of these two charges and these two charges and these two charges. So here we get the system one will be, okay, we will not have the same system, but I am talking about this system now. The system one will be K Q Q prime Q Q double prime R A D plus K Q prime Q double prime between B and D. Okay, it's clear now. As a point C, we have the effect of each charge as a point C. And here we have the electric potential energy of the system equals to U1. Now I want to add, okay, now we have this system, U1 with these values. I want to add a charge here. Let's say we have a capital Q. So I bring this charge from infinity. Okay, it was here. From here to here. This is at infinity, and I put it at VC. And you know, at infinity, we don't have V infinity. I put it at the position C. We can say delta U, the difference of electric potential between the initial and the final, because now we have a new system. It's U2. If I put a charge here, we have U2. Delta U equals to U2 minus U1 equals the added charge times delta V. So delta U equals to U2 minus U1 equals to Q times V final. This is the initial one. This is the final V as a point C. VC minus V infinity equals to O. So equals to Q times VC. This is the difference of electric potential. And you know, to bring a charge from infinity to a point, I need to apply F agent. F agent, the work done to bring the charge from infinity to the point C, I consume F agent, which is equal to delta U. You know, omega FA equals to minus omega F electric. Okay? Omega F applied equals delta U equals to Q times VC. Here we have a very important relation. I resumed all these relations by a simple exercise. Okay, we have these charges. I add capital Q. We have a new system. I want to bring the charge from the infinity to this point. I know the work done by an external agent F equals to the delta potential energy of the system between the old one and the new one. So we can resume here that delta U equals to Q delta V. So delta V equals to delta U divided by Q. Okay, equals to U final over Q minus U initial over Q. And you know delta U equals to minus Q E dot dr. So delta V equals to delta U divided by Q equals to minus E dot dr. This is the most important relation between the electric potential and the electric field. Here we calculated the electric field by using Gauss's law before. Now I want to use this relation to find the electric potential at any point in the medium, in the medium of the charge. And here we have between initial and final state. Okay,